You're listening to DTF for April 10th, 2026. I'm your architecturally load-bearing host, Jack Haxman. We are your daily tech feed for Hacker News, a website where people who build cathedrals argue about bricks. Today's a day for people who chose the harder path and got it right. Let's get into it. I've spent enough time migrating production systems between platforms to know that the hardest part is never the technology. It's the procurement contracts. It's the middle manager who built his entire workflow around one proprietary tool and will mass email the deputy minister if you take it away. It's the 10,000 tiny integrations nobody documented. So when France announces a national plan to move government desktops to Linux, my first reaction isn't skepticism. It's respect for the sheer bureaucratic willpower this requires. Let's be clear about what's actually happening here. The French government isn't doing this because Linux is trendy. They're doing it because they looked at their dependency on a single American software company and asked the question every sovereign nation should be asking. What happens when the terms change? What happens when the licensing model shifts? When the telemetry requirements expand? When the vendor decides your data sovereignty concerns are less important than their cloud strategy? And the answer, as anyone who's been through an enterprise license negotiation knows, is you pay whatever they ask because you have no alternative unless you build one. Run this forward. A government of 67 million people standardizing on open-source desktops doesn't just reduce France's software costs. It creates a massive, well-funded demand signal for Linux desktop tooling. Every bug they fix, every accessibility feature they need, every integration they build. That goes upstream. That benefits every other government, every school district, every hospital system considering the same move. This is how open source wins. Not through ideology, but through one large institution doing the rational thing and creating a gravity well that pulls everyone else along. The comments are telling. Someone from Germany hoping they'll follow suit. Someone noting it works fine for web app workflows, but worrying about power users, and that power user concern is real. But it's also a snapshot of a moment in time. Every year, the gap narrows. LibreOffice handles more edge cases. Wine runs more legacy apps. And the fundamental question isn't whether Linux can do everything Windows does today. The question is whether you want your government's entire digital infrastructure dependent on a company whose interests may not align with yours tomorrow. France looked at that question and gave the only rational answer. The tools exist. The knowledge is available. The real friction was never technical. It was institutional courage. Turns out France has some to spare. Moving on. One of the most provocative comments in the Hacker News thread isn't about NASA at all. It's a commenter paraphrasing a CMU researcher who said that modern Agile and DevOps approaches are challenging architectural discipline. Which, as the commenter notes, is a polite way of saying most of us have completely forgotten how to build deterministic systems. That landed hard, and it should. Consider how a cathedral gets built. Not a modern glass office tower that can be patched and retrofitted and wrapped in scaffolding every few years. A cathedral. You don't ship a cathedral to production and hotfix the flying buttresses when load-bearing walls start cracking. Every stone is placed with the full weight of the structure in mind. Every arch is calculated before the first block is cut. The margin for error isn't thin. It's non-existent. Artemis II in-flight computer is a cathedral. 8 CPUs running flight software in parallel, organized into self-checking pairs, where each pair cross-validates the other's calculations in real time. If one CPU produces an erroneous result, the pair goes silent. It doesn't throw an exception. It doesn't log a warning. It stops talking. This is the fail-silent design philosophy. The ideal that a wrong answer is infinitely more dangerous than no answer at all. The remaining pairs continue flying the spacecraft as if nothing happened, because from their perspective, nothing did. The system runs on Green Hill's Integrity, a real-time operating system built for exactly this kind of deterministic execution. Every process gets exactly the resources it was promised, exactly when it was promised them. There is no garbage collector deciding now is a good time to pause. There is no kernel update waiting to restart. Now, another commenter points out, correctly, that NASA didn't build this. Lockheed Martin and their subcontractors did. That distinction matters for accountability, but it doesn't diminish what the engineering represents. The people who designed this system made thousands of decisions where the easier path was available and chose the harder one every single time. Because when 4 humans are sitting on top of a rocket pointed at the moon, we'll fix it in the next sprint, is not a deployment strategy. We build so much software today optimized for velocity. Ship fast, learn fast, break things, and that works for a lot of what we build. But it is worth sitting with the fact that some of the most important software ever written was built by people who refused to move fast, who understood that the architecture is the product, and who got it right because they didn't give themselves permission to get it wrong. So what happens when you bring that same architectural ambition down to earth to the tools we use every single day? Let me make the strongest case I can for killing MCP. Ready? Here it is. MCP servers are another layer of abstraction nobody asked for. They're middleware. They sit between your agent and the thing it's trying to do. And every layer you add is a layer that can break. A layer that needs maintaining. A layer that adds latency. Skills, on the other hand, are just markdown files. Drop a skill.md into your repo. Teach the model how to use the CLI tools you already have installed. And you're done. No server process, no OAuth dance, no dependency on someone else's infrastructure staying online. The agent uses the same tools you use. It's elegant. It's simple. It's the Unix philosophy applied to AI tooling. That's a genuinely strong argument. And it falls apart the moment you leave your laptop. The engineering insight that MCP gets right. The thing that makes it architecturally superior, despite the added complexity, is the separation between capability description and capability execution. When an LLM calls a skill-wrapped CLI tool, it's doing string interpolation into shell commands running in your local environment. When it calls an MCP tool, it's making a structured request against a defined interface with proper authentication, sandboxing, and versioning. One of these patterns scales. The other is a shell script with ambition. Pull this thread a bit further. Skills require local installation of every tool the agent might need. They require the agent to have shell access. They require someone to write and maintain the markdown that teaches the model the tool's interface. Which, let's be honest, is just writing a PI documentation with extra steps. MCP servers handle all of that on the server side. Update the server, every client gets the update. Deploy it remotely, every device can reach it. The author of the original piece nails this when he points out he can manage his Notion databases from his phone, his Mac, anywhere a client exists. The comments on this one are fascinating because they perfectly illustrate the divide. Solo developers working locally love skills. They're fast, they're simple, they work, and that's legitimate. But the people building systems that need to work across devices, across teams, across trust boundaries, they keep arriving at MCP because connectors are a better architectural primitive than CLIs wrapped in Markdown. This is a pattern we've seen before in software. The simple local solution versus the networked protocol. FTP versus HTTP, local scripts versus AP is, the protocol always wins at scale, even when the script wins at the terminal. The real answer is probably both. Skills for teaching models domain knowledge, MCP for giving them access to services. But if I had to pick one to bet the ecosystem on, I'd bet on open protocol every time. Because protocols are shared infrastructure, and shared infrastructure is how open source wins. 4 stories in, and we're still finding things to celebrate. This one's a security builder throwing their code to the wolves. Every Go binary you've ever deployed has secrets baked into it somewhere. Environment variables, config files, maybe a .env committed to get that. One time nobody talks about. And for years the answer has been, stand up a whole separate Vault cluster. Run another service, manage another deployment, pay another bill, all to store a handful of API keys your app needs at boot. Keeper flips that entire topology inside out. It's an embedded secret store. Emphasis on embedded. Your secrets live inside your process. Encrypted at rest with xchachapoli, -beldi, poli, thor9 poli. Stored in a bool database that ships as part of your binary. No sidecar. No network hop. No separate infrastructure to babysit at 3 a.m. This reminds me of SQLite's trajectory. In 2000, Richard Hipp built SQLite because he was tired of standing up PostgreSQL for programs that just needed a local database. The entire database industry scoffed. A decade later, SQLite was running on every smartphone on Earth. Turns out, most applications don't need a distributed database. They need a really good embedded one. Keeper is making the same bet for secrets management. The engineering here is genuinely thoughtful. 4 security levels, from password-only buckets that unlock at startup. Perfect for automated services. All the way up to remote KMS delegation with mutual TLS for the paranoid and the production critical. Per bucket data encryption keys with proper isolation. A tamper-evident audit chain, the kind of layered design that suggests someone actually thought about threat models instead of just slapping AES on a JSON file. And the best comment in the thread is someone saying, I've been looking for exactly this. I know Vault, I know OpenBow, but they require a separate server with their own infrastructure management. That's the gap. There's an entire class of applications. CRI tools, edge services, single binary deployments. Where running a separate secret server is architectural overkill that teams skip entirely, defaulting to plain text because the secure option costs too much complexity. The author titled this, Help Me Break It. That's builder culture at its finest. Ship it, open source it, invite the community to find the flaws. 1,000 eyeballs on your cryptographic design will always produce a harder system than a closed team reviewing their own work. The code is on GitHub. The invitation is genuine. Go break something. Moving on. What does it actually cost to move a window from one side of your screen to the other? Not in milliseconds. In friction. In the tiny tax your operating system levies every single time you try to rearrange your own workspace. macOS has this animation when you switch between spaces. It's smooth. It's polished. It is, by Apple's design standards, beautiful. And if you switch spaces 40 times an hour, it is maddening. Strip this down to first principles. You have a display. You have multiple virtual desktops. You want to move between them. The actual operation is instantaneous. The system already knows which windows belong where. The animation is purely cosmetic. It exists to make the transition feel physical, grounded, real. Apple is spending your time to sell you a metaphor. The existing solutions are a catalog of compromises. The official answer: reduce motion in accessibility settings. Swaps one animation for another. A fade instead of a slide. You buy. The tiling window manager can do instant switching, but it requires disabling system integrity protection. You're binary patching your operating system to remove a visual effect. Aerospace and Flash Space build entirely separate virtual workspace systems that sit on top of the native one. You're replacing the house to fix a window. Then there's Instant Space Switcher. 1 star on GitHub when the author found it. A menu bar app. No SIP disabling. No replacement window manager. No monthly license. It works by simulating a trackpad swipe with enormous velocity, effectively telling macOS to perform its own native animation so fast it completes instantly. The system thinks it ran the animation. You see no animation. Everyone's happy. This is the kind of solution that only emerges from someone scratching their own itch and publishing the result. Jerpel built this, put it on GitHub, and apparently told almost nobody. The blog author discovered it, wrote it up, and is actively campaigning for people to star the repository so others can find it. That's the entire distribution pipeline. One builder, one writer, one repo. The comments are full of people who didn't even realize the animation bothered them until someone named it. That's how friction works. You absorb it until someone demonstrates what its absence feels like. The tools exist. They've been sitting on GitHub with 1 star, waiting for you to build from source. Moving on. The fundamental problem with Dungeons & Dragons combat isn't that the rules are complicated. It's that they're recursive. A single attack isn't a single event. It's a nested state machine where any step can trigger reactions, and those reactions can trigger counter-reactions. And the whole thing has to resolve in the correct order before anyone actually takes damage. This is a computer science problem wearing a fantasy costume. Alex Losscutoff looked at this and did what any good engineer would do. He wrote a formal specification, not a video game, not a VTT plugin. A model. Using Quint, which is a formal modeling language, he encoded the entire D&D combat system as a state machine, 12 character classes, 14 conditions, legendary creatures, counterspell chains, the full interrupt resolution stack. And that word, stack, is doing real work here. When a wizard casts Fireball, any creature with counterspell and an available reaction can interrupt. That counterspell is itself a spell. So a third creature can counterspell the counterspell. In the spec, this is literally a stack data structure. Push on cast, resolve, pop. It's elegant because it maps the game's actual semantics onto a structure computers already know how to reason about. Run this forward. Imagine every tabletop RPG system, not just D&D, formally specified in a language that supports model checking. You could prove that rule interactions don't deadlock. You could verify that a new subclass feature doesn't create an infinite loop with an existing spell. You could catch the kind of bugs that currently take the community years of play to surface. The rules become auditable infrastructure instead of vibes and errata. What impresses me is the discipline of doing the hard part first. Losscutoff didn't start with the simple cases. He went straight for counterspell chains, readied spell concentration, legendary resistance, the interactions where state machines actually break. The creature spec was 6,000 lines of flat reducer. The combat spec is half that length, but exponentially more complex because it's modeling the space between two systems colliding. The whole thing is open. The spec is published. The demo lets you step through an arcane battle frame by frame. Fireball, counterspell, or a damage death save. Forward and back like a debugger for imagination. One person, building in public, turning thousands of pages of informal game rules into something a machine can reason about. That's the kind of craft that deserves to be found. We've gone from mass spectrometry to D&D rules engines today. Let's keep the range going with some quantum computing. In 1998, a team at Los Alamos built the first working quantum computer. 2 qubits, they solved a toy problem that a pocket calculator could handle faster. The press releases were breathless. The physics was real, but the engineering was nowhere. 28 years later, ETH Zurich just ran a quantum gate across 17,000 qubit pairs simultaneously with 99.91% fidelity. Let's pull this thread. The trick is deceptively elegant. Most quantum computing approaches use superconducting circuits or trapped ions, charged particles held in electromagnetic cages. They work, but they're fragile. And scaling them past a few thousand qubits is an engineering nightmare, because every charged particle talks to every other charged particle. Noise compounds, errors cascade, neutral atoms don't carry charge. They're quieter neighbors. You trap them in optical lattices. Grizz of laser light. And they mostly ignore each other until you want them not to. The ETH Zurich team, led by Tilman Esslinger, figured out how to make pairs of ultra-cold potassium atoms swap quantum states using geometric phase instead of dynamical phase. The difference matters. Dynamical phase depends on intensity, timing, speed. All the things that fluctuate in a real lab with real lasers. Geometric phase depends on topology, on the path the quantum state takes through abstract space. You can jitter the laser intensity. You can vary the speed. The gate still works. It's like the difference between balancing on a tightrope and walking through a tunnel. The destination is determined by geometry, not by how steady your hands are. Now, the Hacker News commenters are right to flag the headline. This isn't 17,000 fully entangled, error-corrected algorithm running qubits. It's 17,000 pairs executing the same gate operation in parallel. That's a crucial distinction. But it's also exactly the kind of distinction that separates vapor from foundation. They didn't demonstrate a quantum computer. They demonstrated a quantum fabrication process, the ability to manufacture reliable gates at scale. And the research paper is on archive. Open, readable, reproducible. The geometric phase technique isn't locked behind a corporate lab or a patent wall. Any group with the right laser setup can build on this tomorrow. The tools exist. The knowledge is available. That's how the bootstrap works. You publish the ladder, not pull it up behind you. Moving on. Peter Levine sits on Git Butler's board now. He also sat on GitHub's board. That's worth noticing. The same venture capital partner who helped guide Git's most successful commercial layer to a $7.5 billion Microsoft acquisition is now funding what the press release calls what comes after Git. The cycle is worth naming plainly. Scott Chaikin is not wrong about the problem. Git was designed for Linux kernel development, for patches over mailing lists, for a workflow where Linus Torvalds personally reviewed submissions. We've spent 20 years building increasingly elaborate scaffolding around that core. Pull requests, CI pipelines, branch protection rules, merge queues. All of it compensating for the fact that Git's mental model doesn't match how teams actually work. Now we're asking AI agents to navigate that same scaffolding, and the seams are showing. The Git Butler CLI looks genuinely good. Branch stacking, intuitive undo, multi-track workspaces, works inside any existing Git repo. These are real problems being solved with real engineering. The team clearly understands the pain. But here's the question nobody in that announcement is asking. Git won because nobody owns it. Linus released it under GPL2. No board, no Series A, no runway, no obligation to generate returns for Andreessen Horowitz. Git became the foundation of all software development precisely because it had no business model. It was infrastructure in the truest sense. A public good maintained by people who used it. What happens when the foundation of your development workflow has a cap table? When the tool that organizes your changes, your agent interactions, your team context. When that tool needs to justify $17 million and whatever comes after. The Git Butler source is available today. But source available and community owned are different things, and the difference matters exactly when it becomes inconvenient for the investors. Scott says GitHub never lived up to social coding. He's right, but the reason it didn't is instructive. Once the acquisition closed, GitHub's incentives shifted from serving developers to serving Microsoft's platform strategy. The tool didn't change, the ownership did. I hope Git Butler builds something extraordinary. The CLI suggests they can, but the blueprint for foundational developer infrastructure already exists, and it doesn't involve a 16-slide pitch deck. It involves publishing the code and walking away from control. That's how Git won. That's how Linux won. The pattern is not ambiguous. Now, from building tools that navigate code bases to navigating actual deep space, Artemis II is heading for the moon. I once spent 3 months building a sensor calibration pipeline where the hardest lesson was that a single number is almost never the truth. You measure one thing, you think you understand the system, and then the edge cases eat you alive. That experience is why this Artemis Zurich story hits different for me. NASA just sent 4 humans beyond low Earth orbit for the first time since Apollo, and yes, the photos are stunning. Reed Wiseman captured Earth lit by moonlight, with auroras threading both poles in zodiacal dust, glowing in a triangular wedge. Gorgeous. But the payload that matters most is invisible. It's the radiation dosimetry. Here's what makes space radiation genuinely hard to engineer around. It's not one problem. It's 3 overlapping problems. You've got trapped particles in the Van Allen belts. Intense but brief. You punch through them. You've got solar particle event. Intermittent, operationally urgent. They can spike dose rates over hours. And then you've got galactic cosmic rays, which are the real monster. High-energy heavy ions present all the time, and nearly impossible to shield against because the physics works against you. Heavy shielding can actually produce secondary radiation that's worse than what you blocked. An absorbed dose alone tells you almost nothing. A gray of protons and a gray of heavy ions do completely different things to biological tissue. Dose rate matters. Particle direction matters. Organ depth matters. The crew is wearing personal dosimeters, carrying organ-specific chits, giving blood and saliva samples. Running cognitive performance tests. They're building a multidimensional map of what deep space actually does to a human body. The time is clever too. Solar cycle 25 just peaked, which means lower galactic cosmic ray background but higher storm probability. You get to characterize both threat profiles in one flight. Now, every piece of this data will be published. NASA radiation science is open. The models, the measurements, the biological correlations. Anyone building spacecraft, designing habitats, planning Mars transits can use it. That's the difference between a space program and a space product. When the architecture of knowledge is open, every future mission gets safer. Every engineer on Earth can run the numbers. The blueprints for keeping humans alive in deep space belong to the species, and Artemis II is generating the dataset that makes that real. Open blueprints for surviving deep space, open tools for creating art. Pause the pattern holds everywhere worth looking. One commenter mentions they ended up studying under Frieder Nake, one of the actual pioneers of computer art from the 1960s, and it changed their whole trajectory. Another commenter built a fourth-like language just to control the generation process. A third moved from processing to P5.js to raw Rust shaders. Every single one of them discovered the same thing independently, and the author nails it. Every algorithm you learn becomes a tool you can reach for later, and over time, those tools accumulate into something like a vocabulary. Pull that thread all the way out. If every algorithm is a word, then a programmer who learns enough of them eventually has a language, and a language implies something dangerous. It implies you might have something to say. That's the comedy buried in this piece. The author starts in 2016 treating generative art as a programming exercise. Find a formula, tweak parameters, save it, move on. Pure math tourism. Then texture shows up, then color, then composition. And somewhere around sketch 60 or 70, the realization lands. This isn't illustration anymore. You're making choices. You have taste. You accidentally became an artist while trying to understand a sunflower. The author now has a personal library of simulated materials. Watercolor washes, dry brush strokes, cracked glaze, none physically accurate, all expressive. All built by hand through hundreds of iterations. Published openly on P5Js, where anyone can read the source, fork it, learn from it. That's the part worth celebrating. This entire artistic vocabulary developed in public, on an open platform, where every sketch is both artwork and teaching material simultaneously. 114 sketches over 8 years. Each one a small experiment in what code can feel like when you stop optimizing and start listening. The tools were always free. The math was always available. The only thing that took 8 years was learning to see. This has been your daily tech feed for Hacker News for April 10th, 2026. This podcast is entirely AI generated. Scripts by Claude Opus 4.6. Voiced by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something worth sharing and put your name on it. We'll see you back here tomorrow.